Hi, this is Professor Fernandez. We are going to work on class note C in lesson 17. In this class notes, I want you to picture a pendulum that is hanging from a wall. So it looks something like this. And what we are going to do is we are going to think about and calculate really and interpret the equilibrium solutions to this system. And of course, relate them to what we would think of as equilibrium if we saw a pendulum in a lab. So this setup here tells us that the equation of motion of the pendulum is this. What is theta? Theta is the angle that the pendulum makes with respect to the vertical axis. And g here is the acceleration of gravity. L is the length of the pendulum. It is actually the only parameter that matters for this equation of motion. The mass does not. There are m's hidden everywhere in this equation. They've just canceled out. So that may be surprising, but insofar as we care about this angle changing, the mass does not matter. So let's look at part A. This part of the question asks us to say, well, if I assume this substitution, which again is the same substitution we've been using in lesson 14, if I use x equals theta, y equals theta dot, and I use that to convert this ODE, show that I get this system. So let's do that first. So A. So if x is theta and y is theta dot, let's do our usual dance here. X dot is theta dot, which excuse me, is equal to y. Great, so my first equation in my system is x dot equals y. And then if I go down to the second equation, I have y dot would be theta double dot. And that's where I'm going to go up to the original ODE up here, and I am going to solve for theta double dot. So theta double dot equals minus g over L sine theta. Okay, so minus g over L sine theta. But I know that theta is x. So I'm going to insert that in here, minus g over L, excuse me, sine of x. So that's my second equation in my system. Great. And this completes this part of the example. You can see that we have derived the system up here. So we've now converted one second-order ODE into a system of two first-order ODEs. This is not a linear system because of the sine x that makes it a non-linear system. So you can expect there are going to be some rich dynamics here for a pendulum, and again, you might not think that when you see a pendulum swinging, it's nothing exotic. But mathematically, it's actually very, very hard to write down the actual solution to this system or to this ODE. You do not get a very simple function. So one of the reasons that's one of the reasons why I had said in the beginning of this lesson that we think about equilibrium solutions to begin with, right? Nonlinear systems, generally hard to find explicit solutions for, but with equilibrium solutions, those are explicit solutions. And they're also nice from a physical perspective because they have a nice physical interpretation. So let's find the equilibrium solutions for this system, and then let's interpret them physically. So I am going to remove everything here, make space for our interpretations. And then we'll talk about what those equilibrium solutions are. All right, so as before, to ensure that we are looking at an equilibrium solution, we want the right-hand sides of both x dot and y dot to be 0. This one gives us a fairly, immediate condition. Y has to be 0, and we're going to go back and interpret that in terms of the pendulum in a minute. This one gives us the condition that sine of x has to be 0. Okay, so that does require a little bit of solving. What x values work there? Well, sine of 0 is 0. Also sine of pi is 0, but also sine of negative pi is 0, as well as sine of 2 pi and negative 2 pi. So you can see the pattern here. So x equals n pi, where n is an integer. So this funny looking z stands for the set of integers, 0, plus and minus 1, plus and minus 2, plus and minus 3, and so on. So now we have found the equilibrium solutions. So I'm going to put them in vector form. So equilibrium solutions. what do they look like? They look like x of t. They don't have any t's because they're equilibrium, but I'll put that in anyway, equals, well, the first component of these vectors is x, and that is n pi. The second component of these vectors is y, and that's 0. So these are the equilibrium solutions to the system. And now let's interpret them. So I'm going to put a little n over here so that I can index them by the n value that we're choosing. So let's just look at x sub 0 of t. So that would be n equals 0. And then let's look at x1 of t. So that's pi 0. And then let's look at one more, x2 of t, because you'll see what happens in a minute, 2 pi 0. Okay, so excuse me, what I want to do now is use the fact up here that x is theta. So every single one of the components here, up here, is a theta value. And then y is theta dot. So every single one of the components here is theta dot. Theta dot is how theta changes in time. So for all of these equilibrium solutions, right, theta dot is 0, which is telling us that the equilibrium states of the pendulum are characterized in part by the pendulum not moving, which, again, is not a deep statement. But as I said in the previous video, we are showing mathematically that at least according to this model of the pendulum, we are figuring out exactly what the equilibrium solutions are. So in all of these equilibrium solutions, the pendulum is not going to be moving. You can kind of already, if you imagine the dynamics of the pendulum, you can kind of already foresee what the equilibrium states are going to look like. But anyway, okay, so great. We get that the pendulum is not moving. That's what this second component tells us. Second component being 0 tells us. What about the first component? So theta is the angle. It's the angle measured with respect to the vertical axis. And it's measured in this, excuse me, counterclockwise fashion as usual for angles. So if I were to draw the picture corresponding to pendulum not moving and angle of 0 degrees, right? What does that picture look like? It looks like this. That's the pendulum. If I drew this picture, angle of pi and not moving, it would be like if I took this pendulum and I swung it all the way up, right? So it would be the pendulum where it's vertically upward. And then if I took this one, angle of, because this is an angle of pi, 180 degrees. If I took this one and angle of 2 pi, I would kind of start here and then let it swing all the way back down to where it started from. So the picture here would be the same as it was in the x sub 0 case. It would be a pendulum just hanging that way. All right? And you can convince yourself that if I were to keep writing vectors, so, equilibrium vectors, equilibrium solutions here of the same form, n pi and 0, these pictures wouldn't change. I would either get this picture or get that picture, right? You can also convince yourself that if I used a negative n value, right, then I'm just measuring, instead of theta going that way, I'm measuring it going this way. But, this is still theta equals 0. This would be theta equals negative pi, so we're back to this picture. And then this would be theta equals negative 2 pi, so we're back to this picture. All right, so we don't learn anything new from all the other equilibrium solutions that I'm not writing. Right? What we do learn is that every single equilibrium solution represents, just for this system, just one of 2 possible physical states. And here they are down here. It's when the pendulum is just hanging out, hanging, and not moving. And it's, this difficult thing to achieve if you take a pencil and you put your palm out and you put the pencil at the center of your palm to try to balance the pencil perfectly so that it doesn't fall. Right, this is the other equilibrium state that we're picking up on. You might have noticed right there that I just talked about, essentially stability, which is another concept in differential equations. That is not one that we are going to talk about in our course. Some of that information is in the textbook that we've been using along with this course, so you're free to take a look at that. But these two are the only equilibrium solutions for this model of the pendulum. They are not the same in that stability case, right? If you were to give this pendulum here a little nod, a little kick to the right, it would just kind of oscillate around that equilibrium point. If you gave this pendulum here a nod, it would kind of go very quickly away from that equilibrium point, and it may never return, depending on how much of a kick you give it. Anyway, that is a concept that, again, I just wanted to point out and make some connections with some physical dynamics that you might have already played with, like a pencil balancing it on your palm. But we've done what this example asked us. So we've interpreted the equilibrium solutions physically. We've certainly calculated them. And all of this, again, came from a second order ODE that we converted to a system of two first order ODEs.